All right, let's dive into the second half of the TLS 1.3 handshake. You click a link, your browser starts talking to a server, but how can you be sure it's the real server and not some imposter? Well, today we're going to decode that digital handshake and see exactly how a server proves it is who it says it is.
And really, this is the most important question in all of internet security. Think about it. You've just created this amazing secret language with a server. But what if you're speaking that secret language to a bad guy? Then all that security is for nothing. This whole problem is called authentication, and it's exactly what these next server messages are built to solve.
So, here's our game plan. First, we'll see the moment the conversation goes dark and becomes encrypted. Then we'll check out the server's digital ID. It's like a passport. After that, we'll see how it actually proves it owns that passport. We'll finish with a final confirmation, and of course, the key things you absolutely need to remember.
Okay, first up, at this point in the handshake, the client and the server have already figured out their shared secret keys. So from here on out, everything, and I mean everything, they say to each other is completely scrambled. To anyone trying to eavesdrop, the conversation just went dark.
And what this means, technically, is that all the handshake messages that are left get stuffed inside this secure encrypted wrapper. It's like putting your mail inside a locked box before you send it. This makes the rest of the conversation totally unreadable to anyone on the network. It is now a completely private channel.
All right, on to our next section. Now that the communication line is totally secure, the server can send over some extra details without worrying about prying eyes. You can kind of think of it like passing notes in class, but only after you're sure the teacher can't see what you're writing.
So the server sends this message called encrypted extensions. It's full of configuration details that, weren't absolutely necessary to set up the encryption keys in the first place. By waiting until the channel is secure, TLS 1.3 really boosts privacy. It stops network spies from picking up little clues about how the server is configured.
And now we get to the main event, proving identity. How does a server actually prove it's, say, Google.com, and not some convincing scam website? Well, it does this by showing your browser its official digital passport.
This digital passport has a proper name, an X509 certificate. It's a standard format, and just like your own passport, it's not something the server can just create itself. Nope. It has to be issued by a trusted third party, which we call a certificate authority, or a CA. This little document is basically the foundation of all trust on the web.
So if we take a closer look at this digital passport, it's actually pretty simple. The subject is just who it belongs to, the website. The issuer is that trusted authority who handed it out, like a company called Let's Encrypt. The validity period is just the expiration date. It also has the server's public key, which is super important for the math that's about to happen. And maybe most importantly, it has the issuer's digital signature, which proves the whole passport isn't a fake.
And here's a perfect real-world example. You can see right here, this certificate was issued to hsalpsig.de, that's our subject, and look who it was issued by, R3/Let's Encrypt, that's our issuer. It's exactly like looking at the details on a driver's license.
You might be wondering, though, how do we even trust the issuer? Well, that's where this chain of trust comes in. Your browser, Chrome, Firefox, whatever you use, comes with a pre-installed list of top-level, super trusted authorities called root CAs. So this image shows that the website certificate was signed by R3, and R3's authority was signed by an even bigger root authority. It all changed back to a source your browser already trusts from the get-go.
Okay, so the server just showed us its passport, but anyone could just steal a passport and show it, right? Just having it isn't enough. So this next step is absolutely critical. The server has to prove that it's the legitimate owner of that ID.
The first part of this proof is pretty straightforward. The server sends the server certificate message. This is literally the server just handing its passport over to your browser for a look. Your browser can now check all those details we talked about, who it's for, who issued it, and if it's expired.
But now for the real magic trick, the certificate verify message. This is where the server does something that only the true owner of the certificate could do. It performs a cryptographic calculation to prove it has the secret private key that's paired with the public key inside the certificate. This is the step that completely stops an attacker who just copied a certificate.
Now, if you're studying for a test, pay close attention to this slide. This difference is so important. The certificate message is just showing the ID, but the certificate verify message is proving you are the person on that ID. The analogy is perfect. One is just presenting your passport, the other is providing a unique signature to prove it's really, truly yours.
So how does it pull this off? Well, the server takes every single message that's been exchanged so far in the handshake, and it creates a unique digital fingerprint of that entire conversation. That's called a hash. Then it signs that fingerprint using its secret private key. Your browser can then use the public key from the certificate to check the signature. If it checks out, it's mathematical proof that the server has the secret key and is who it claims to be. Pretty cool, right?
We're so close to the end. The server has proven its identity. The communication channel is secure. There's just one final check to make sure nobody, like a man-in-the-middle attacker, has been messing with the conversation transcript along the way.
And to do this, the server sends one last handshake message called the finished message. It's a lot like what we just saw. First, the server gathers up all the handshake messages. Second, it creates another one of those unique cryptographic fingerprints, a hash, of the whole conversation. And third, it sends that encrypted fingerprint over to the client.
Now, here's the kicker. The client does the exact same calculation on its end. If the fingerprint it comes up with is identical to the one the server just sent, it's confirmation. It proves both sides saw the exact same handshake and that no messages were added, removed, or changed in transit. This guarantees the handshake's integrity.
Okay, let's wrap all this up. If you're studying this stuff or just trying to get your head around it, these next points are the absolute most important things to lock in. This is the stuff that really matters.
Remember these 3 things. 1, the certificate message is for presentation. It's just showing the ID. 2, the certificate verify message is for authentication. This is the big one. It proves the server owns the secret key. And 3, the finished message is for integrity. It's that final check to make sure nobody messed with the conversation. Presentation, authentication, integrity. If you get those 3, you've totally understood the core of how a server proves its identity online.
And that's it. The digital handshake is officially complete. The server is authenticated, the communication channel is encrypted, and it's protected from any tampering. So the secure tunnel is built. What do you think is the very first thing your browser sends through it? Think about it, and we'll see you next time.